Hello everyone, welcome back. Today we want to learn about the definite integral. So our goal is to understand what the definition of definite integral is and how it relates to the area of the curve of the graph of a function. Also want to understand some basic properties of definite integrals. And see also related to properties of derivatives, and also find the exact areas in a curve, certain curves using geometry. So first, I'll remind you what a Riemann sum is. So you may have seen my previous video dealing with this, or you may have seen another class, another video. But think about the area under a curve. So let's come over here. We have some curve that maybe looks like this. And then we have a point we're going to call A and B. The goal is to estimate this area under the curve of some function f of x. Okay, and that's what we're going to see is called the integral. Now, a couple ways to do that. One way to do that is something called a Riemann sum. So the idea, I can show you the picture, it's probably better to start with that. Let's say this is our function, kind of similar to what you see on the right. So the idea of what we do is actually estimate that area using rectangles. So I'm going to divide my function from goes to A to B up into basically n rectangles. So the way to do that then is choose my n, it can be whatever you want. Okay, it could be 2, 10, 20, whatever, or more. And then use my endpoints, b minus a. That length divided by n will give me n lengths. Each we're going to call width of delta x. That's the width of each one of these rectangles. Okay, so that's the width of each rectangle. And we're also dividing this interval up into n values, basically. So a starts at x0. Then we have x1 is where my first rectangle goes from x0 to x1. The second rectangle goes from x1 to x2 and so forth. As you can see in the middle from xk minus 1 to k. Each one of those width is delta x. It goes up to xn. And then the way I get my height of the rectangle is where this rectangle intersects where it crosses the function value. I can do that any point in between these x values. Typically, it's done in the middle, like you see right here. Okay, in this one from x1 to x2. Could be done at an endpoint in the left side or the right side of the rectangle, or any point in between. I just have to use those rectangles. And also in general, and what we're about to talk about, you don't necessarily have to use rectangles of the same width. That's usually the way it's done. But basically, you're going to add up all the areas of all those rectangles. That's going to give you an estimate of the area under the curve. As you can see, this is not going to be exact. There are places where the rectangle is above the x-axis, above the graph where it overshoots, or places where it's below the curve where it undershoots. So there's going to be error there. But the way to fix that error is to have more and more rectangles in this method. So that's the idea of a Riemann sum, adding up those rectangles. Now, finally, let's introduce what's called the definite integral. Okay, so as I said, the more of those rectangles you use, then the more accurate this becomes. And so if we take the limit in this as, think of this as two ways. Limit either there's number of rectangles goes to infinity, or which means the same as the limit as your delta x width of each rectangle goes to 0, and that will give you the exact area under the curve. Okay, let's come back over here and write that down. So if we define the definite integral, which is equal to the area under the curve of f from A to B, that's equal to, you use this notation, it's called integral notation, it's called the definite integral. And you may have seen indefinite integrals when we talk about antiderivatives, and they are related to this. But there are no bounds in here. Here we have the bounds. So from A to B, this is where we put our bounds of our interval, okay, of our function f of x. And then finally this dx, and what this dx means is this idea of a differential. And you've seen the idea of differential before, is basically if you take the limit as delta x goes to 0, then delta x goes to the differential d of x, and this is equal to the limit. And one way to write this is that where the delta goes to 0 of this Riemann sum in sum notation. So remind what this means. Let me write it down first. Okay. So remember, the sum notation just means we're going to add. So what this means, we have the same thing written here. Okay. So the delta xk, that's the width of my rectangle. And just by the k meaning they could be different widths, although typically they're the same. The f of xk, remember xk is some number in between. For example, here xk minus 1 and k. It's some number in between those two values. And that's where I get the height of my rectangle. It'll be any point in between. Okay. And then you take the f of that, gives me the height of the rectangle. This is the width of the rectangle. And so this sum notation means I start at 1. So when k is 1, I replace the k's with 1. So here, I'd have it x star of 1 and delta x, that's the height and width of this rectangle. Then add, the sum means add to that, then go to k equals 2. Go to the second rectangle and replace the k's with 2's. So x star 2 is the height right here of the second rectangle, and so forth till I get to the nth one, the last one. Okay, so this limit just means take the limit as this delta goes to 0. Okay, and basically this becomes the integral. Okay, let me also mention here, as I didn't write this down, the limit is also this delta goes to 0 of delta x sub k is equal to this differential x. So basically it's taking that and squeezing it to basically 0 width. That's the differential d of x. Okay, and this is what's called the definite integral. Definite because I have these bounds, so I have a specific area. Indefinite just means you're just taking, essentially find the antiderivative. And we'll see in a future video how the antiderivative and the definite integral are related, and they are. In fact, that's one of the most important parts of calculus, but not today. Won't see that. But a definite integral is where I have bounds. I'm looking at a specific interval from a to b. Okay, so that's what happens. So let me show you something on Desmos. This is something that I didn't do, but someone else did on Desmos. If you just looked up Desmos Riemann sum, you'll find this. This kind of shows how this works. So what we see here is this curve, our function f of x. It says this function is sine of 2x plus x over 3. Once again, I didn't make this up. Someone else did. And basically, you have some options here you can change. You can change the endpoints. I'm going to leave those as they are for a and b. And I will change the number of intervals. And this final thing right here, this I, the sum, gives us basically the value of our integral, the area under the curve. And also remembering, or also realizing if you haven't seen this before, that area above a curve is positive, or area above the x-axis is positive, area below the x-axis is negative. Okay, that shows the green here is positive, the red is negative. Okay, so right now we have 3, which n is 3. Okay, so we have 3 rectangles estimating this. You see, it's not a very good estimate. Okay, this part right here that's on this side of the curve is an error. This part's here below the curve. This part white here is missing here, and here is also an error. But that's what we have. Okay, and right now this is the value, essentially the approximate value of this integral between my bounds, which are -1 to 3. Okay, now let's see what happens as I increase n. Okay, as n essentially goes toward infinity, we're not going to go that far. As n increases, that's going to increase the number of rectangles. That's going to make the width of my rectangle get smaller. And so as we'll see, that's actually going to increase the accuracy, as you can see visually, and also see what happens. And our value will kind of start to approximate a limit itself. Okay, so let's increase it. You see, so basically, more rectangles. You notice my value now it's positive. All right, so increase it to about 30. Okay, our value is now about 0.51. Okay, about 0.52. Okay, you see it's much better than the original one with just 3. Okay, 10 times as many. Okay, let's go to 50. rectangles. Okay. Now value is about 0.56. I don't yet know what the value is, but we're getting closer. Okay. Let's go to about 75. And this number is going to start to settle down to something, I think, close to 0.6. Let's go to 75 rectangles. Okay. Right. You see, that's a pretty good approximation right now. Still a bit of error. You can see a little daylight, a little white here left, and also a little red here where it shouldn't be. About 0.59. Let's go all the way to 100. Okay. As you can see, it's settling down. Let's take it to about 0.6, maybe 0.61. So let's just look at the bottom number here, the total, and look at that from about 50 to 100 and see what happens. So go back to 50. As I move in this direction, as it increases, my width of my each rectangle is getting smaller. My accuracy is increasing. You see this number is starting to settle down to about 0.6. Okay, it's changing, not a whole lot, mostly in the smaller decimal places. So expect the true value is probably about 0.6, 0.61, something like that. Okay, and now the idea of the limit, of course, is I would keep on until I have an infinite number go toward an infinite number of rectangles, which means that each rectangle essentially has a zero width. And then basically that will give me the exact value, the exact area under the curve. And we'll show you in a future video how to find the exact value of the curve, not using rectangles, but actually using the antiderivative, but not today. Also, one more thing I didn't mention is this also, I believe, yeah, right here, we can also choose we want a left-handed, right-handed, or midpoint Riemann sum. Here it's at left-handed, okay? But actually that doesn't really matter. And I'll show you why. So let me show you one more thing. Let's go back to 3, okay? Right here, right, I'm the left-handed sums. Each one, the value of the height of the rectangle is at the left of the interval. And so as I can change this, I want to do 1 for a right-handed sum. Okay. Now you notice that value is at 1.8. Let's actually go to the same thing, go to 100. And it should be very close to the same value we saw before. Okay, it's actually a bit larger, about 0.68. Okay. But it's pretty close to what we saw before, okay, with the from 1. And actually, let's do one more with the midpoint. Let's go back to 3, as low as I can get it. Midpoint is 0.5 for C. Okay, you see it's each one. It's evaluating the height of the rectangle, the midpoint, or it's using the midpoint of the rectangle to give us the height of our rectangle, where it crosses the function. And once again, if I go to 100, it's going to be a bit different. It's a little bit, but still very close. And so actually what also happens in the limit, it doesn't matter where you take your height of the rectangle from, the limit is going to go to the same place because your width of your rectangle is going to shrink to 0. All right, so that's the idea of a definite integral. So this is how you find the definite integral, is take the limit of these Riemann sums as the width of the rectangle. Let's think of either the number of rectangles goes to infinity, or the width of the rectangle, each rectangle itself goes to 0. And that gives us the exact area under the curve. Okay, now let's do a couple things. Let's actually practice approximating some areas under curves, but not actually using Riemann sums. We'll also want to use just geometry. Before we get to that, let's do one more thing. So let's talk about some properties of integrals. Let's actually do that right here on the next page. Let's talk about a few properties of integrals. Okay, I took this basic table out of a textbook. And basically it shows some common properties of integrals. Okay. Now the first one, we'll illustrate some of these. First one says that if you take the integral from a to a of f of x dx is equal to 0. Hopefully that makes sense. Let's graph this. So we have some function, some function or f of x. And if I just here at a, all I have is this little line. So remember, the width of that rectangle is 0. So here, my d of x, delta x, which is equal to my d of x, is basically 0, approximately 0. So there's no width to that rectangle. So the area under that is 0. Okay. Also, what this tells us, if the area under a point, an individual point, is 0. Okay. So the point has no width, has no length or width or anything. So the area of an individual point is 0. Okay. What also that implies, if I have a function that's discontinuous, if I say had a hole in my graph right here, that wouldn't change anything. My area would be essentially the same because the area of an individual point is 0. If I had a hole in the graph here, that would still not change my definite integral or my area. Okay. Now, number 2 is something it's kind of hard to explain. We'll just have to leave that as it is. But basically, you can also, sometimes that's useful to say that the integral from definite integral from a to b of f of x is equal to negative if you switch your bounds going from from b to a. If you reverse the order of your bounds, it's the same as the negative from a to b, the negative in the correct way. All right. Now let's look at a couple more here. All right, number 3. Let's talk about that one. Okay, so number 3 says this. So the definite integral from a to b of we have f of x plus g of x. It says plus or minus g of x dx. I can actually break these up. And these rules are very similar to what we see with integrals. Or sorry, we see with derivatives. The derivatives, you know, if you have the derivative of a sum or difference, you can break those up. And the same thing here. And that's reason because of that is because, as we'll see in a future video, there's definitely a connection between definite integrals and the derivatives related to the antiderivative. But we'll see that in the future. So f of x dx plus or minus a to b of f of x g of x dx. Okay. All right. Actually, let's see. I actually need to pause this just a second, so shouldn't notice anything, but I'll be right back. Okay. So I did pause it just a second. You probably didn't notice much of anything, but let's take a look. So this one, let's do kind of a very basic example. Okay. So just do a couple essentially horizontal, a couple constant functions. So if right here, this constant function between a and b, if this is f of x, okay, and let's say right here, as we go up a bit higher, so if I add something to f of x each point, this is f of x plus g of x, okay, then basically that's the same I make these pictures a little bit smaller, but hopefully you get the idea. If this is f of x plus and this is my function g of x. Basically, what this means is just these, and we're doing this for rectangles to make it easier to understand, but it works with other more complicated functions as well. All that better. So basically, I add these areas together, f of x and f of x plus g of x. This whole area is the sum of these two areas right here. That's basically what that's saying. It's also true of subtraction as well, if I subtract one from the other. Okay. And then finally, the last one. 4 is also a property like a derivative. It's a little harder to draw, but you get the kind of the same idea. Okay. Of property number 4. So I guess I can do that real quickly as well. So this one says if we have the definite integral of a to b, we have a constant times our function, f of x times d of x. We can pull the constant out front, and that's just c times that integral. Okay. And once again, if I kind of draw a basic example of this, and once again, I'll just use a constant function to start off with to make it a little bit easier to see. But if this is my function f of x, and let's say this is 2 times f of x, that area under the graph would be the same as 2 times just the small area by itself. Okay, that's all that's saying. Then the last one is also really useful. 1 is one of the most useful ones. So this one, the very last one, says if I have the definite interval from a to b of f of x dx, okay? And also I have, this is equal to the definite interval from a to p times f of x dx plus the integral from p to d, or p to b, rather, f of x dx. Okay, well, what you have then is p is in between a and b, okay? And all this says, think about any function, if this makes sense. So here's a, here's b. Let's say p can be anywhere. Let's say it's right here. Let's say it's closer to a than it is to b, though it doesn't matter. Okay. If this is area 1 and this is area 2, as you can obviously see, area 1, this is area 1 right here, and area 2, area 1 plus area 2. Then you're in the curve from a to p plus the area of the curve from p to b. So it should look more like a p, is equal to the total area. This is the total. Okay, that's all that's saying. So you can actually divide up that anywhere you want in between, and if you add that up this way, you still get the same area. Okay, now to wrap up, let's do an example or a couple examples, a few examples of actually finding, in this case, we want to find the areas under curves using geometry. So what we don't want to do is not going to use the Riemann sum. We're just going to use geometry to help us out. Okay. So let's look at this one. Number 1. So let's say we're doing an interval from the definite interval from 1 to 10 of f of x dx. And here's what fx is going to be. It's going to be a piecewise function, and basically 3 pieces. Okay. So the first part is 4x if x is between 0 and 2. Right, better if. Let's say if that's the case. Then it's negative 8x plus 16 if x is between 2 and 3. And here, not including the 2, but including the 3. Once again, I have to make sure to include in both endpoints the same one. It wouldn't be a function anymore. There's just going to be a constant negative 8 when x is greater than 3, or if x is greater than 3. So let's use Desmos to help us kind of graph this, to get an idea what this looks like. And what we're going to see is it's something that's easier to not actually use Riemann sums or rectangles. I can add up a sum of, break it up with a Riemann sum, we do it differently. Okay. Now I put all these graphs on here. Now I can't really easily do a piecewise function on Desmos, at least not easily, but we'll get the idea. Okay. So y equals 4x. That's the first part. Y equals negative 8x plus 16. And then the last one y equals -8. And that one we can't even see. It's off the graph there a bit. Okay, actually it's at 3. So here's my graph. Okay. Now, a couple things to notice. So here, the first one, 4x, okay, it starts at 0, 0, and it goes from 0 to 2. So at 2, goes from 2 to 8, okay, and it includes 2, point at 2, at 2, 8. Let's draw that. Let's go back to our picture and draw that, okay? Make a drawing, help us with this. Okay, this first section goes from 0, 0 to 8. And right here, this point is included, okay? Now, the second part is the second graph. It goes from 2 to 3. So let's put this. Here's 2. Here's 3. Then we're going all the way to 10. Okay. Now, here, let's go back to Desmos, find out what that is. Okay. So this one at 2 goes from 0 to 0 to 3, -8. Okay, so 2, 0 to 3, -8. This point is not included. This one is. Zero. I don't, oops, made a mistake. I should have. Crap. I'm going to do that, but that's okay. Okay. Actually, 2, 0, it's actually an open circle. And it goes to 3, 8, 3, -8. And this is not going to be the best graph, but you'll get the idea. 3, -8. Okay. And then finally, it's a constant. Then it goes all the way from here to 10. And so that is going to be 10, -8. Okay. Now, that is want to find the area under this curve. This area here and here. Okay. Now, hopefully what you notice then is we have a few shapes here we can work with. Okay. We have 2 triangles and a rectangle. Okay. This triangle, okay. Remember for, it's the base, the length, the bottom. So the base is 2 and the height is equal to 8. Okay. So the base, with the base, it's 2. And actually it's a right triangle. This is as well. And the height is 8. Okay. Now this triangle right here, okay, its base is just 1, but its height is also 8 because it goes down from 0 to -8. Okay. And here, then, of course, you have a rectangle. This rectangle. So here, the length is going to be from 3 to 8. It's going to be 7. And we're going to call that the width. Doesn't matter what you call the width or height. The width is also going to be 8. Okay. Now, so if you remember, the area of a triangle is 1/2 the base times the height. Okay, and that's actually true of any triangle, not just the right triangle. 1/2 the base times the height. Okay, so we have 3 areas. Okay, so let's call this like area 1, area 2, area 3. Okay, so our integral from 1 to 10 of, wait a minute, 1 to 10? Oh, crap. Actually, hang on a second. I think I wrote it as 1 to 10. Let me change that then. Let me make it 0 to 10. It's easier to work with. If you did 1 to 10, that would work. This would be like a trapezoid and not a triangle. But let's make this 0 to 10. Because yeah, I actually had this one 0 to 2 anyways. Let's make this 0 to 10. My fault. Okay, that's going to work, make it easier. All right. So from 0 to 10, f of x times dx, okay? And that's going to be equal to, I'm calling area 1 plus area 2, second triangle plus area 3, okay? The rectangle. So we just add those up. Let's find those and add those up. And we can do it separately or here, okay? And so that's going to be, area the first is going to be 0.5 or 1/2 times the base times the height. So here, the base and the height of the first triangle was base 2 times 8, okay? The second triangle was also 0.5, the base times the height. The base of that was 1 times the height, which was 8. And then finally, our last one, the length and width was 7 times 8. No, apostrophe times. Okay, let's figure out what this is. All right, so 2 times 8 is 16. Half of that is 8 plus 8 times 0.5 is 4. And then 7 times 8 is 56. And so that should be 68. So that then is the area, the integral, the value of that integral from 0 to 10, f of x dx. Oh, wait, hang on, crap. I forgot something. Notice what did I forget? I wasn't being careful. Yeah, these are actually negative areas, right? These areas here are negative, okay? Because these are under, so let me say that. So areas are negative because they're under the x-axis, okay? I wasn't being very careful, was I? So we can fix that. And because we have to make that correction because they're below the x-axis, okay? The base thing was, once again, think about like the Riemann sum. We did a Riemann sum of this. Our function value would be negative here. The area have a negative height for each rectangle, but make that a negative area. Okay, so now that's going to be negative 60 and 8, which is going to be negative 52. So I actually have a negative area. That's interesting. Okay, negative 52. That's okay. All right. And if you want to think of, once again, think of what that can mean in real life. Well, if integrals are an accumulation of something or adding something up. So if you're adding something up in a negative, that means you're losing something. So for example, if this was if you had like maybe a bucket, okay, you had water coming into the bucket, and you also had a hole in the bucket, okay, then think about the rates of things coming in versus going out. If you add all that up, then it's possible at the end of some amount of time, the level might have increased if you have more water coming in than going out, or the water level might have decreased. You might have lost amount of water in the bucket if you had more going out than coming in. That'd be like the case here. So negative here in this case, think about the idea of a bucket with a hole in it and a water coming into it and out of it. At the end of some amount of time, we have more water going out. We're losing more water for that amount of time. Okay. All right. So that's the idea. And so every now and then we can do that if we have a nice function where we can actually get geometric shapes. Sometimes we can find an exact area, which is good. This is actually an exact area, not an approximation of Riemann sums. This is pretty rare, but still it's useful to do a few of these like this. So let's review what we've talked about so far today. So we introduced the idea of the definite integral. So if you take a Riemann sum like this, and basically you, as your number of your rectangles goes to infinity, or based on meaning the same thing as the width of each rectangle goes to 0, then you'll actually get not just an estimate, you get actually the exact value of the area under the curve. Take that limit as, in this case, we define the limit as delta goes to 0. The limit essentially is the width of a rectangle goes to 0. Then the delta extension becomes the differential d of x, dx, and basically that becomes what's called the definite integral, the exact area under the curve. In the future, then, we'll see how we relate this area under the curve to antiderivatives. Then finally, look at some of the properties of definite integrals and relate those to some of the properties, especially these properties 3 and 4 are essentially the same kind of properties work with derivatives, and that makes sense because integrals basically are antiderivatives, so they have similar properties. Thank you. Have a good day.